Okay, let's dive in. We're going deep today on an idea that's, what, nearly 80 years old now?
Just about, yeah. Mid-1940s.
An architectural blueprint from John von Neumann and his team that, and this is the crazy part, still defines pretty much every computer, every smartphone, every server you touch.
It really is wild when you think about it.
We're talking about the von Neumann architecture. You might also
Yeah.
hear it called the Princeton Architecture. And its influence is just, it's permanent.
It's an incredible topic because it gets to this core irony in computing history.
With that?
The very decision that gave us the flexible general-purpose computer we know and love today, this idea of a stored program, also, baked a critical, persistent problem right into the foundation.
And that problem is the infamous von Neumann bottleneck.
Exactly, the bottleneck.
So that's our mission for this deep dive. We want to understand the genius behind that original design,
Yeah.
but also pinpoint exactly where that choke point is.
And then look at the decades of engineering workarounds we've built just to manage it.
It all starts with one core idea, right?
It does. The stored program concept, it sounds so simple to us now, but back then it was completely radical.
So what is it, fundamentally?
It just means that the program's instructions, the to-do list for the computer, and the data that those instructions need, they're stored together
In the same place.
in a single unified memory unit.
And you have to remember the context of the 1940s. This wasn't just a small tweak. It was a revolution. Before this, you had machines like the ENAS.
Oh, yeah. Lena.
Or you had totally separate storage for programs. And to run a new calculation, engineers were physically, plugging in cables, flipping switches, rewiring the machine.
That is the key context. The stored program concept meant you could change what the machine did just by loading new information into memory, not by getting out a screwdriver.
It's the birth of software.
It is. The birth of software as we know it. It made the computer universal, programmable.
So that's the big idea. Let's get into the physical blueprint it created. We need to go back to those mid-1940s design notes and talk about the core components. Because the problem is, well, it's structural.
It's entirely structural. If you look at the design, it's defined by 5 specific functional units. They actually called them the organs of the computer.
The organs. I like that.
Yeah.
So what are these 5 parts that make up this, 80-year-old blueprint?
Well, the first 2 parts are what we'd now just call the CPU, the central processing unit.
Okay.
You've got the central arithmetic unit that does all the math addition, subtraction, all of the logic.
The calculator part.
The calculator part, yeah. And then you have the central control unit. That's the part that reads the instructions and, directs the traffic. It's the manager.
The brains of the operation.
The brains, exactly.
Okay, so that's 2. What's the third?
The third is the most critical one for our discussion, the memory. And like we said, this is the unified spot for both the instructions and the data. Everything gets pulled from this one pool.
Yeah, and the last 2. I'm guessing they have to do with getting information in and out.
You got it. The fourth organ is the outside recording medium. Think of it as permanent storage.
Like a hard drive.
A hard drive, an SSD, yeah. And the fifth is the input-output mechanisms, the specific channels for moving data between that central memory and all the external stuff.
It's a really clean model when you lay it out. The
Yeah.
CPU, the memory, and the I/O. But the devil's in the details, right?
Mm-hmm.
How do the CPU and that memory actually talk to each other?
And that is where the weakness appears.
I figured.
Because the instructions and the data share the same memory, they also have to share the same communication route to the CPU.
A single road.
A single road. It's called the Common Address and Data Bus. It's one shared highway for absolutely all traffic, whether that traffic is a program instruction or the number that program needs to add.
And that single highway is the bottleneck. It has to be. Which, okay, brings us to part 2. Let's define this von Neumann bottleneck, because it sounds like the simplicity of the design created just mandatory traffic jams.
That's a perfect way to put it. The bottleneck is a direct result of that contention on the common bus. To really get it, you have to think about how the CPU works, the fetch, decode, execute cycle.
Right. Walk us through that cycle and show us where the jam happens.
Okay, so every single thing your computer does, step by step, requires the CPU to first fetch the next instruction from memory.
Okay, so that uses the bus.
It uses the bus, then it decodes that instruction to figure out what to do. Now, if that instruction involves data like, say, add number A to number B, the CPU then has to go back to memory to fetch that data.
That uses the bus again.
It uses the bus a second time.
So for just one simple operation, the CPU has to use that single shared road at least twice. Once for the instruction and once for the data.
Precisely. And because the instruction fetch and the data fetch both need that single common bus.
They can't happen at the same time.
They cannot occur simultaneously. They are forced into a line. The instruction has to be fetched and delivered before the request for the data can even be sent out.
It seems almost laughably inefficient. If the fix was so obvious, just give instructions their own road and data its own road, why didn't they do that? What were the constraints back then?
That is a brilliant question, and it gets to the heart of the trade-off they made. What you're describing, separate memory and separate buses for instructions and data.
Yeah.
That's a real thing. It's called the Harvard architecture.
So it existed. They knew about a faster way.
They did, yeah. It was used in some early, very specialized calculators. But the Harvard model, while faster, is much less flexible.
How so?
It's great for things where the program doesn't really change, like in digital signal processing. But the von Neumann model, by putting everything in one memory space, made the hardware way simpler, and more importantly, it made the machine general purpose.
You could run any program you could imagine.
Any program. That flexibility, that universality, it came at the cost of speed. The bottleneck was the price they were willing to pay.
An acceptable price for creating the modern computer.
Yeah.
But how bad is that price today? How much does that limitation really cost us now?
It's more dramatic now than ever, and that's because of the massive gap that's opened up between how fast a CPU is and how fast memory is.
The processor got way, way faster, but the road to memory didn't keep up.
Not even close. CPU speeds grew exponentially. But the time it takes to get one piece of data from main memory, the latency has improved much, much more slowly. We're talking gigahertz in the CPU, but a trip to memory can cost hundreds of those clock cycles.
So in the time it takes the CPU to just grab one number from memory through that bus, the processor itself could have done hundreds of other things if it just had the data on hand.
That's the perfect way to quantify it. The CPU is constantly starving. It's waiting for either the next instruction or the next piece of data because the highway is just too slow compared to the city it's feeding.
It doesn't matter how fast your car is if you're stuck on a single-lane road in rush hour.
Exactly.
And this problem, this restriction, it must become absolutely critical when the computer is dealing with the outside world. Let's move to part 3 and talk about I/O, input-output operations.
This is where the bottleneck stops being a theoretical limit and becomes a very real problem you can actually feel.
Okay, give me an example.
Think about a huge data transfer. You're copying a massive 4K video file from your computer to an external drive. Or you're downloading a giant game over the network.
These are I/O operations.
Right. And they involve these slow peripheral devices.
Slow compared to the CPU, anyway. A spinning hard drive or a network connection is moving at a glacial pace.
Glacial is the word.
Yep.
So when the CPU kicks off that huge transfer, the I/O system has to move this enormous block of data into or out of that unified memory, and that process completely monopolizes the common bus.
The whole road is shut down just for this one slow-moving convoy.
That's right. That fifth organ, the I/O mechanism, it demands total control of the bus to shift this block of slow data.
So what's the super-fast CPU doing while this is happening? It gives the command to transfer the file, and then it just has to wait.
It's forced to wait, or what we call busy waiting. While that bus is tied up with the slow peripheral, the CPU can't get new instructions from memory. It can't get new data to work on. The communication line is totally clogged.
And that waiting time, waiting for a mechanical drive to spin up or for a network packet to arrive, that just crushes the system's overall efficiency.
Severely. The whole system's performance drops.
Okay, this sounds like a system designed for maximum frustration. If the flaw runs this deep, how do our computers work at all? This must be why I/O management is so incredibly important.
It absolutely is. I mean, forcing a multi-gigahertz processor to just sit and wait for a mechanical device it's just unacceptable from a performance standpoint.
So we had to invent workarounds.
Essential workarounds. This fundamental architectural limit is precisely why we developed sophisticated I/O management techniques.
Let's talk about the biggest one, direct memory access, DMA, because that sounds like it changes who's in charge of the highway.
It does. DMA is an elegant solution to this monopolization problem. Instead of making the super smart, super fast CPU manage every single byte of data being moved,
You delegate.
you delegate. You introduce a separate, dedicated piece of hardware called the DMA controller.
A traffic cop.
Dedicated traffic cop, exactly. The CPU basically just gives the DMA controller its orders. It says, here's where the data starts in memory, here's the device it's going to, and here's how much data to move.
And then the CPU is free.
And then the CPU can just walk away. It's free to go and process other tasks, completely removed from the slow, tedious job of managing the transfer.
So the DMA controller takes over the bus, handles the whole block transfer between the peripheral and memory by itself.
And it only bothers the CPU once the entire job is done. It sends a little signal and interrupts saying, hey, I'm finished.
That is clever. The bus is still clogged, but at least the CPU isn't stuck in the traffic jam with it. Its time is salvaged.
That's the genius of it. You minimize the performance loss by delegating the weighting to a specialized, dumber chip. And there are other techniques too, like buffering and interrupts, that all do the same thing. Manage the traffic so the CPU only has to pay attention when it's absolutely critical.
It's just this constant battle then, a battle against a ghost in the machine. We're always trying to maximize the efficiency of this single-lane road without ever being allowed to just build more lanes.
It really is. We're constantly innovating in software and in hardware to compensate for a decision made in the 1940s that chose flexibility over raw parallel speed.
This has been a fantastic deep dive. Let's try to synthesize the key takeaways here.
Sounds good.
The central contradiction we're left with is that the very foundation of modern computing, the stored program concept, is both the source of its incredible flexibility and the source of its biggest performance limitation.
Yes. By forcing data and instructions to share a memory and a bus, the von Neumann architecture created its own bottleneck.
And as we've seen, that means that all this complex I/O management, things like DMA, they're not just fancy features. They are essential workarounds to keep the processor from grinding to a halt.
Necessary patches on a foundational design?
And I think understanding this really changes how you should look at computer performance.
Yeah.
It's not just about raw CPU speed. It's not just about gigahertz. It's about how the whole system manages the flow of traffic on that single shared highway.
That's the critical insight. You can have the fastest CPU in the world, but if it's constantly waiting for data, it doesn't matter. Memory access latency is often the bigger performance hurdle today than the raw processing speed.
Which brings us to our final provocative thought for you to think about.
Okay.
The stored program model is defined by this consolidation of instructions and data and the shared bus that creates the bottleneck.
Yeah.
So what would a computer system look like if it fundamentally abandoned that concept entirely?
We touched on the Harvard architecture with its separate pathways, but that's very specialized.
Right. But imagine a true general-purpose system that completely segregated them, that fully embraced parallel pathways to finally, once and for all, kill the von Neumann bottleneck.
What would that even look like? How would it manage memory? What new trade-offs in complexity or cost or even programming difficulty would we have to accept to get that speed?
Something to think about the next time you're watching that progress bar slowly creep across the screen during a big file transfer.